So, chapter 3 and chapter 4 are all dealing with derivative and using the derivative. Now doing the opposite, antiderivative. An antiderivative is kind of called what's an indefinite integral or indefinite integration. It means we're not defining it. We're not going to say integrate from here to here. We're just saying integrate just in general. We will get to definite integrals, and in fact, that's a good portion of that part of calculus. So yeah, basically we started with the original, went to the first derivative, second derivative, and so now maybe I'll give you the first, second derivative. We've got to get back to the original. The second bullet there is pretty important. When taking an antiderivative, you must write plus a constant or plus c at the end, and I'll explain why once we do a couple of these, why you really kind of have to add that in there, especially if it's an indefinite integral. The little note there says when we took derivatives, we basically, the power rule said to multiply by the exponent and then subtract 1 from the exponent. That's what we did, right? The power rule, multiply out front and then take it down a power. Well, here we're going to basically do the complete opposite, which is first add 1 to the exponent and then divide by the new exponent. And I hope you can see that's the exact opposite, doing it completely in the opposite order. Not just part of it but completely in the opposite order. So here we have this little symbol out front, looks like almost like an S. It does kind of mean summation, but we'll just leave it as the integration symbol for now. It's saying basically integrate 2x with respect to x. And that's good that the variables are the same. So what we're going to do is the 2, you can throw the 2 out front if you want or just leave it there. So here's your 2x, right? What power is on the x right now if we leave it in this integration over here? 1. And what does this tell us to do? Take it up a power. So it was 1, so now make it 2. Okay? And now divide by that new power. So you're going to divide by that exponent of 2 plus some constant. Well, now the reason I gave you all these 2's in the very first one is to see which ones, if you could tell me which ones actually do cancel. Yeah, pretty much the exponent one doesn't count here, right? But it can do that. So x squared plus some constant. And now we're going to take a slight break here and explain why we have the constant on there. If I had just, go ahead. Very good. That's exactly what it is. What was said is that, let's say I gave you x squared plus some number. Doesn't even matter. And I asked you to take the derivative. It would be 2x plus nothing, right? Because the derivative of any constant is nothing. So is 2x the derivative of x squared plus any number? So are there a lot of answers really to this problem? X squared plus 7, x squared minus 13, x squared plus 1.7. All of those are possible answers. Instead of writing them all, we just say x squared plus some constant number. Can that constant have a variable on it? Well, no, because then that's a different problem, right? The derivative would be different. So that's why we put the constant on there, basically because then we cover all of them. All of those ones I just said have 2x as a derivative. Okay? And that's why it's the opposite. So here we have a 3. So the 3 is just a constant, so you just leave that there. X, take it up a power, so third. Divide by your new power. 3, once again, I want to see if you can tell me what actually cancels in, what does not. Very good. We have to put plus a constant. No. I was just waiting to see if somebody would say it. So these 3's right here do cancel, so it is x to the third plus some constant. Again, because that could be x to the third plus any number, and the derivative would actually be 3x squared. Okay? Now, obviously, not all the time are things going to cancel like that, and so I gave you letter C over there. I'll show you what some people do on, I'll wait for that. So it's 7x to the second over plus something, yep, constant. And anything you can do there? Not really. Might as well just leave it like that. And I'm hoping that you see is that really is the complete opposite of what we've been doing, because now if we go back and do these derivatives, we actually come back to where we started. They should undo each other. Okay? Or if you integrate and then take the derivative, you should get kind of back to where you started. Okay, they should cancel out. As anything in calculus, it's very helpful. Basically, chapter 5 in this school from algebra 2 is hugely important. Being able to manipulate things so that the derivative or antiderivative is easier. And they call that rewriting it. So how could I rewrite 1 over x to the third to make it a little bit easier to work with? Yeah. Close. X to the negative third dx, right? Now, am I actually allowed to go ahead, take it up a power, and divide by my new power? Could I really do that at the beginning here? Not really, because it's in the denominator. That's not going to work so well. But now I can go ahead and take that up a power. Now be careful. A lot of people mess up. Very good. X to the negative 2 is up a power, right? Divide by negative 2 plus some constant, right? And now we probably should simplify. You noticed why eventually with derivatives we started simplifying things because we were setting it equal to 0, doing all these things. And so we should probably get this fairly neat as well. Now a lot of people tell me that that negative and that negative cancel. And that is not the case. That negative in the numerator means that x is unhappy. Okay? And so if we had to simplify this, I would put the negative, I would put this particular negative on top, but you don't have to. Here's how I would write it. Let me put it that way. That's how I would write that one. Do you have to write it that way? No. There's nothing wrong with writing it that way. Okay. But I normally like my numerator to be, if there's one that has to be negative, I would prefer that the numerator is, because it saves me a lot of trouble. So that's how I would write it, but if you put it on the bottom, it's just fine. So that would be a very good simplified answer for that one. Is there a question? Because people often will forget to distribute if there's another negative in the problem if it's only in the denominator. Yeah, some people, you can do that, definitely. Some people prefer, because they know they're going to mess up, they just do it like that. Yep. I would prefer you do that or put it in the numerator. Don't leave it in the denominator. It's not wrong, but it is opening up yourself for mistakes later. How about rewriting this next one? X to the 1/2. Very good. Now, am I allowed to take it up a power and do all that? Yeah. And I'm going to actually integrate and then I'll do the simplifying. You're going to get really good at these and you're going to kind of do it all in the same step. But for your first one you see, it'd be helpful if I do it this way. So let's take it up a power. 3/2. Very good. But now you have to divide by 3/2, right? That's your new power plus a constant. Now here's something that you're going to get very, very good at. I know you don't believe it right now, but dividing by 3/2 is the same as multiplying by 2/3, right? So a lot of you are just going to start doing this. Oh yeah, I got x to the 3/2, and instead of writing over 3/2, you're just going to multiply by 2/3. Okay. Because again, dividing by 3/2, same multiplying by the reciprocal, which is 2/3. Again, that's another thing from algebra that can save you a lot of time. So those two at the end there are very, very good answers. Here's where I was going to wait. I was going to tell you something earlier, and I chose to wait till now. Whenever you have things multiplied like this is just kind of one term, right? 2 sine of x dx, it's all just kind of one term. If it's ever multiplied just like that and it's just one term, what you can do, if you wish, I don't know why I put parentheses around that, but anyways, that's an S, a really bad one like that. Whenever it's multiplied, like you can pull the whatever you're multiplying by out and just integrate what's left on the inside. So there are a few problems we could have done that one on earlier. Okay, we could have done that on basically any of these three. but we didn't really need to because they were pretty simple problems. The only reason I would choose to do it here is it's the first time you've seen trig for integrating. Now you could look at your little table and it would tell you what it is. But let's look at it this way. The derivative of sine is cosine, right? The derivative of cosine is negative sine. So I need something that when I take the derivative of it, I get sine. That's the tricky part. No? What's that? Negative cosine. Very good. So it's 2 times negative cosine of x. That's constant. Do you agree? Now let me tell you one more time. If I take the derivative of just cosine, what do I get? Negative sine. So what if I take the derivative of negative cosine? I get a negative sign, which is a positive sign. Now if you look at your little chart I gave you earlier, it's probably right on there. The integral of sine. Isn't it on the right side? Which number is it? Yes, it's number 6 on your little chart there. The integral of sine is negative cosine. But I wanted to see if you could kind of follow that through. Now here is where a ton of people do all this hard work right and then they simplify it wrong. Anybody brave enough to share what they believe the simplified version of this answer is? Yes. Very good. Negative 2 cosine x plus a constant. So what do people do wrong? Yeah, they just do 2 minus cosine, right? Well, that's not what that says. It says 2 times a negative cosine, right? So it is a negative 2 cosine of x plus a constant. Very good. So if you ever really get stuck on a problem, you can refer to that chart there, and it should help you a little bit. But again, it kind of helps to try and think of where it's coming from. Any questions so far? So it's the opposite. So the easy thing on these is that you could check them easy enough. Just take the derivative of your answer, and you better get back to where you started. Here's a few interesting ones. Any ideas on A? Yeah, because now how'd you do that? Were you thinking of something that you could take the derivative of and get 1? Well, isn't that an easy way of kind of thinking about it? And it is x, but let's think about that, why that works. Because what I'm really asking you to integrate is 1x to the 0, right? Isn't that really what I'm asking? That's one way you could write it. It's a really strange way of writing it, but you could. And then if I want to now, let's take that x, take it up a power. So it was 0, so you take it up a power is 1 divided by new power, 1 plus some constant. But again, I want you to think, beyond just stuff like that, what would I have to take the derivative of to end up with 1? And it's x. Has to be. So x plus a constant. Very good. When we took derivatives, the plus in between terms didn't really matter, right? You just did them separately. Same thing, just do them separately. That's the nice thing about this. You don't have to worry about it. And some people write it like this. They'll actually write integral of x with respect to x plus the integral of 2 with respect to x. It should be the same answer. Okay. So how about if we integrate x? So it's something that I have to be able to take the derivative of and end up with x. Or you could just do this antiderivative. So it's x to the second over 2 plus, now we got to do this one, so it's 2. So what would I have to take the derivative of to get 2? No, just close. 2x, right? Again, if you got lost, you could say, what if it's 2x to the 0, right? Take it up your power, divide by your power, but it is 2x. Yes, it's just plus 1 constant, though there is always that question. Oh, you have 2 integrals there. Should it be 2 different constants? Nope, just 1. Just a constant is fine. Yeah, you can write over 1, sure. Yep. If that helps you remember that you did that antiderivative, leave it there by all means. And let's face it, if I do take the derivative of this, it'd be 2x over 2, which is x, right? This derivative of 2x is 2, and the derivative of some constant is nothing. So I do actually get back to that if we turn around and take the derivative. I hope you figured out by now that we can continually take antiderivatives as long as we want, right? just like you could take derivatives as long as you want. But some antiderivatives are obviously much more complicated than others. Try letter C right now on your own, please. Well, let's see how you did. So you could separate them, and I noticed some of you as I went around didn't even bother with that, which is fine. And so basically you just took the antiderivative of this. Well, the 5's right there. X to the 4th over 4 plus there's a 2. X to the 3rd over 3 plus x to the 2nd over 2 plus a constant. And any constant you want. Eventually, we are going to find out exactly what that constant has to be, but I have to give you more information. I have to say, I want this to happen, I want this to happen, go find the constant. Okay, and there will be a particular answer, but right now it could be anything. Okay. And don't worry about that stuff in the red over there, that'll be later. Letter D. Looks very, very complicated. It really isn't, because of algebra. Any ideas? Yes. We could bring the radical up to the top, but then have we really dealt with any multiplying yet? And we haven't had any, and we haven't talked about any products or quotient, and they've all just been added, right? We've done like 3 times something, but not a variable times something. Yeah. We are definitely going to eventually do that. Yeah, make x to the 1/2 on the bottom. Definitely. Here's a really neat trick that a lot of people forget about and a lot of people do wrong. Right? You can actually split it up like this. It's basically somebody's already gotten me a common denominator. I'm just splitting it up. That's all I'm doing. Now, please do not do it. Here, now, whatever you do, don't do this problem over here. Because here's what people start doing wrong. They see a problem like that, and then you see how I just flipped it over. And then they start doing this. Not the same thing. Okay, so maybe if you think you're going to do this, make a note off to the side that you can't do that. Okay. You can't just split up a denominator if it's like this, but if it's in the numerator, you can, and you have a monomial on the bottom, you can do that. But this one over here, a big no-no. Okay? So don't do that. Now, the suggestion from somebody was to write this down here as x to the 1/2. Let's see if that helps. Because right now, let's face it, did either one of these get any easier to do by this little rule we learned today, take it up a power and all that good stuff? Not really. But we're not done with algebra. Can we simplify just that term? Because this is x to the 1st over x to the 1/2. They have the same base, don't they? And what are you supposed to do when they have the same base and you're actually dividing them? What do you do with exponents? Subtract. So it's 1 minus 1/2 is 1/2. Plus, well, what can I do with that one so that we can use this rule that we just learned today? It's kind of what somebody said earlier. We just couldn't use it when they said it. Yeah. Make it unhappy. Move it to the top. Now, is there any multiplying anymore? No. Any dividing anymore? Not really. That's just sitting there saying, go ahead, take it up a power, divide by your new power. So this term, if we take it up a power, it's x to the 3/2. Now remember that deal? You're going to divide by 3/2, but really that's multiplying by 2/3, right? Plus. Now this is where a lot of people will make a mistake on this one. X to the, very good, 1/2. But then it's dividing by 1/2, which is the same as multiplying by 2. That's much less scary than it looked like at the original. Yes? Now you said 2/3. Is that just a mistake on your part, or you mean like this? Yep. Yep. Yeah, you can leave the 1 down there. Again, if that helps you remember that you actually did it, by all means leave it there. Yep. So that wasn't too bad. Why do I have another slide? Oh, it's blank. All right. So based on what you've seen today, yeah, certain functions are going to be more problematic than others. We have little rules for those. Can you think of a function that could possibly cause a problem with integration? The function I'm asking you to find is, let's look at it this way. Was there a function that when you took the derivative of it, the derivative seemed to have nothing to do with the original? Or which function can't you take the power up 1? Well, e to the x is an easy one. If it's its own derivative, it's also its own antiderivative. So you got to love e to the x. Yeah, what about natural log? When we took the derivative of that, it was 1 over x. So 1 over x is the function that is going to be a slight problem, but you already know the answer. It's just I have to show you how that works. The antiderivative of 1 over x is the natural log. Okay? And here's why it's a problem. Because really, it's, if you rewrote it, it's x to the -1. Take that up a power for me. Divide by your new power. Uh-oh. Okay. And so that's why that one has a very specific answer. The integral of that is the natural log of x. Okay. Any other questions?